Got it. So good morning, good afternoon, good evening, and welcome to the 5th seminar of the International Journal of Multi-Phase Flow Spotlight Seminar Series. This will be
Ted, people have not been let in yet.
Oh,
yeah, now
okay.
Just wait for a minute, maybe.
Yep, thank you very much. Sorry for jumping the gun.
Yeah.
Yeah, I'll wait one more minute or so. Okay, well, I'd like to get started then. Good morning, good afternoon, good evening, and welcome to the 5th seminar of the International Journal of Multi-Phase Flow Spotlight Seminar Series. This will be our last seminar for a few months as we take a break for summer, and we will return in September with a new slate of speakers. My name is Ted Heindel. I'm with the Center for Multi-Phase Flow Research and Education at Iowa State University, and it's my pleasure to introduce today's speaker. Nathaniel Mashikion obtained his PhD in 2014 in the physics laboratory of ENS Lyon, where he studied the dynamics and heat transfer of large particles in turbulence. After his PhD, he studied inertial waves in turbulence and rotating fluids, thanks to a postdoctoral fellowship at the FAST laboratory at Paris-Sud University. Nathaniel then did a postdoc at the University of Washington in Seattle for 3 years, where he helped with the coordination of experimental research to establish multiphysics controls in the gas-assisted atomization through a multidisciplinary university research initiative funded by the Office of Naval Research. He is now at CNRS researcher at Légy in France, a large research lab dedicated to the fluid mechanics and investigation of a wide variety of geophysical and industrial problems. His research focus is on turbulent and multi-phase flows. Today, Nathaniel will talk about multi-scale characterization and feedback control of spray formation in a two-fluid atomizer. So Nate, it's all yours.
Thank you for the kind introduction, Ted. Good morning, good afternoon, and good evening, everyone. And I want to thank you for attending my talk, and I hope that you will enjoy it. I also want to give a special thanks to the IJMF organizing committee to give me this amazing opportunity to present my work. So today I will present a spray formation mechanism in a two-fluid atomizer, and I will focus on a multiscale characterization of the near field, and I will touch briefly on feedback control. So the IJMF community is well aware of the importance of liquid gas flow, both in nature and in engineering application. And among those applications, I'm interested in sprays. That is a cloud of droplets, liquid droplets in a gaseous environment. And there's many ways to obtain a spray. The one I will focus on today is called gas-assisted atomization, where the destabilization and breakup of the liquid phase is largely due to a gas phase. There are many applications of coaxial atomization, and to name a few here, you can see atomization along with combustion, which is important for the propulsion industry, or it's used in jet engines. You see here a pharmaceutical application with the fabrication of tablets, and here you see an application of coating for the manufacturing industry. So I will review a few key mechanisms of gas-assisted atomization, and we are going to consider coaxial atomization for the rest of the talk, where you have a liquid jet that is surrounded by an annular gas jet that I also call a co-flow, as the gas is flowing along the liquid jet here. So if we look right at the exit of the atomizer in a region that is called the near field, The spray formation happens thanks to interfacial instability that destabilize the liquid interface and lead to primary breakup events, which create liquid inclusion, such as film, ligaments, droplets, and drops that can be also not spherical here. And then if you look at those liquid objects in this turbulent gas jet, they are going to experience secondary breakup events and are going to be dispersed by this turbulent flow. And very far from the atomizer, in a region that we call the far field, where there's no more breakup events, you have small spherical droplets in a turbulent flow that further disperse, and their mass and heat transfer can be very important for certain applications too. So now let's focus a bit on a breakup mechanism, and we can first consider a very simple situation where we have a spherical droplet of diameter d being suddenly subjected to a gas flow at a certain velocity ug, and a lot of different breakup morphology can happen for this simple situation, and this is well parameterized by the Weber number that compares the stresses induced on the drop due to the gas flow compared to the surface tension force that is trying to keep it together. And in this situation, you can see the Weber number that is directly proportional to the square of the gas velocity here. And in a situation of low to moderate Weber number, the drop first gets flattened by the fast airflow that then blows a bag in the drop that can also be called a membrane. And this film is going to grow thinner until it bursts, leading to very small droplets, and the rim yield much bigger droplets. At higher Weber numbers, so for instance, for higher gas speed, when the drop is flattened, it's subjected to a transverse instability that yield small drops here. So let's see how this happens in coaxial atomization. You can see here two subsequent snapshots of this liquid jet being destabilized, and you see the formation of bag here with this bag growing. And here what you can see is the remnant of the rim of a bag that dropped into like this string of droplets that get dispersed in the next picture. And we can look at that dynamically thanks to this high-speed imaging movie. And you see the formation of bags. And fairly often, those bags form on those interfacial perturbation that grow along the side of the liquid jet. And several mechanisms for those perturbation has been proposed. The most agreed upon is a Kelvin-Helmholtz type instability due to those interface aligned with a gas shear. So you have two interfaces flowing at two different velocity that gives those typical roll-ups that you can see in many applications. And other instability are proposed for atomization mechanism, and one of them is a Rayleigh-Taylor type instability that we are typically more familiar with it when we have the presence of a heavy fluid on top of a light fluid, where it yields those very famous digitation here with those plumes that you can see here, where it's gravity driven. But this also works when you have an interface that is being accelerated instead of just a gravitational acceleration. And so this can happen for this drop being accelerated. And the proposed scenario for spray formation is that so the Kelvin-Helmholtz type instability is going to lead to those perturbations that are going to grow and get stretched into ligaments that are more or less transverse to the gas flow and get accelerated and break into this Rayleigh-Taylor type instability. And this is a very efficient regime of atomization called fiber type atomization, where the drops are being peeled from the edge of the liquid core, and you can see that happen in this high-speed movie here. extensive research has been dedicated to characterizing atomization regime, and this is summed up here in this phase diagram from another review, where you see here the liquid Reynolds number, so increase of the liquid injection rate, and here the gas Weber number, increase of the gas injection rate. And for today's talk, I'm going to focus on a fixed liquid injection rate in laminar condition with a Reynolds number of about 1,000. So that places us here, and we're going to increase the gas velocity to go from this bag or membrane breakup regime that you see on the picture on the left to the fiber type atomization that we see on the right. And on top of that, I'm interested in the role of swirl, which is the addition of angular momentum in the gas co-flow. So you get, instead of just a purely longitudinal gas jet, you get a swirling jet. And this is present in a lot of applications, such as found in propulsion, for instance. What's been clearly identified in the literature is that beyond a critical value of swirl, you get dramatic effect on the spray. And this is characterized by a swirl ratio, that is the ratio of the angular to longitudinal momentum. And you see, for instance, a snapshot of low momentum coaxial spray here, below the threshold of swirl, and here above the threshold of the swirl. And it's hypothesized that there's a vortex breakdown mechanism of this swirling jet that lead to a recirculation that largely explains the spray and give this very different morphology. So what's been also noted by this group or other is that the increase of the swirl ratio tends to lead to a decrease of the droplet size in the far field, so far from the atomizer, as you can see on this graph here. And what we're going to be interested in today is to try and do a thorough quantification of the effect of the swirl in the spray near field, to try and go a bit beyond qualitative imaging here. So before diving into the near field, I just want to give an overview of experimental techniques that we use to characterize the spray, to go from the near field where droplets are being produced to the far field where we look at this cloud of droplets. So so far, I've been showing high-speed imaging, which is a very useful tool to characterize the near field. And here is another picture where you can see those bag breakup phenomena. And in the far field, to characterize the spatio-temporal distribution of droplets, the community relies a lot on a laser interferometry technique, which is called particle phase Doppler anemometry, that gives you the size and velocity of passing droplets in the crossing of two laser beams. So the combination of those techniques are really useful to characterize the whole cascade of mechanism happening in coaxial atomization. And they're also useful to help validate the development of numerical simulations that can tackle the near field physics or the far field physics, as they are, as it is typically difficult to have a simulation that tackles everything due to the large scale separation in this turbulent multi-phase flow. And I just want to highlight here the fact that there's no the emergence of simulations that can that, as they can't tackle everything on the same grid. What is done is that the different physics are solved in different grids that are then put together to do a handshake and have a simulation of the whole spray, as you can see here with a recent effort by Olivier Desjardins' group at Cornell University. And so you will need both experimental, the data from both experimental techniques to try and validate those simulation development. So I'm going to close this parenthesis and dive into the near field, where the metric that has received the most attention in the literature is what is called the liquid core length, and can also be referred as intact length sometimes. So this corresponds to the longitudinal extent of the part of the liquid jet that's still fully attached to the nozzle. So you can see that with the schematic, you have this liquid jet that's atomized and broken up, and you take the part that's fully connected, and you take its longitudinal extent. And this metric is important for many applications, such as propulsion. And it's been studied very early on. You can see this very nice result from this group in the 90s, where they look at the mean liquid core length as a function of the gas Weber number, so increase of gas flow, where you see kind of as expected with a physical intuition that the higher the gas speed, the shorter liquid core length can be maintained as atomization become more and more efficient. And when you fix the gas speed but increase the liquid injection rate, so increase the liquid Reynolds number, you can now maintain a longer and longer liquid core length. And despite this early work being done with only several still photograph, the researcher noted that they were able to see fluctuation around the mean of this quantity that reach up to 15%. Over the range of conditions explored. And it's only recently that researchers have tried to tackle the complexity of this fluctuating quantity. And you have this group from IIT Madras, for instance, that reported the probability density function of the liquid core length. And there's also a recent effort by the group at Imperial College that reported data on the time dynamics, the temporal dynamics of this metric. So in the first part of my talk, I am going to focus on this aspect by doing a large-scale description of the near field using high-speed imaging with visible light. And this corresponds to work that I did when I was a postdoc at the University of Washington, working in Alberto Zaliceda's group. And in the second part of the talk, I am going to focus to a bit more detail of the near field in this region that's highlighted here, using Synchrotron X-ray to probe the physics of the near field. And this work was done at Argonne National Laboratory with Alan Castangren, and was done jointly with Ted Heindel's group from Iowa State University. So for the duration of the talk, I am going to be using a coaxial, a canonical two-fluid coaxial atomizer that is schemed here, that is open source and available to the community, where you can see the link here. And there's both the machining procedure and the full geometry that can also be used in numerical simulation. And in the simulation I showed before from Olivier Desjardins' group, this is the geometry that is being used. So liquid flows in the center of this round pipe to yield a fully developed laminar poiseuille flow. And this liquid nozzle is embedded in the gas nozzle that has inner and outer wall that are cubic spline shaped to produce this turbulent annular gas jet. There are many non-dimensional parameters that characterize the problem, but today I will only vary the gas speed. So I only need one parameter, and I will talk in terms of momentum, gas to liquid momentum ratio, which is a ratio of the dynamic pressure of the gas to the one of the liquid. So it goes as a velocity ratio square here. And we're going to go through a wide range, 1 to 200, due to the wide range that can be found in different applications of coaxial atomization. And as I said, I am interested in the effect of swirl on atomization. And so if we do a transverse cut of this atomizer in the inlet plane, you can see in black here four inlets that are on axis to produce a purely longitudinal gas co-flow. And there's also 4 tangential inlets, so off axis, to produce this swirling jet. And when we use swirl, the tangential flow rate is taken from the, so we just keep the total flow rate constant so that the momentum ratio stays the same, and we characterize the swirl by a swirl ratio that's just a ratio of the tangential to the axial flow rate, and that is varied between 0 and 1. So here are two high-speed movies that I've been showing before, and they are side by side so that we can well see the difference in both spatial and temporal scale. And one thing that we can notice, and that I mentioned before, is large-scale instability of the liquid jet. That is called the flapping instability. That is this hindering motion that here with the backlit imaging, we see it projected as a motion of left to right, typically. And we see that here at lower momentum ratio in the membrane breakup regime, this can typically lead into the formation of this hook-like feature that can help the production of bag, while at higher momentum ratio, we mostly see the signature of the flapping as the fact that this jet is kind of spreading closer to droplet left and right, left and right. So from this movie, the first thing that we can do to kind of get an idea of the large-scale description of the near field is to produce mean intensity map. So by just averaging this image, but here we are not going to average directly the grayscale image. We're going to use thresholding to get a phase indicator, as you can see on this picture here. Where it's black is where liquid is present, while it's white, there's no liquid, so it's only the gas phase. And of course, backlit imaging doesn't tell you anything about the quantity of liquid, but it does tell you whether or not there's liquid here obscuring the beam of light. And so if you average this, you can obtain a liquid presence priority map, as is displayed here, where values in yellow correspond to a priority of 100%, so liquid is always there. The dark blue is 0%, you never observe liquid, while values in the green here of around 50% would be liquid being there every other time. So now from this map, we can draw a transverse profile at different downstream locations, here going from black to red. And you see the priority decreasing on the center and increasing on the edge due to the spreading of the liquid. And on top of that, it's hard to see, but you have a dashed line that corresponds to Gaussian fit. And that tells you that the liquid presence priority profile is self-similar. And from those Gaussian fit, we can retrieve the standard deviation at each downstream location. And I report here plus and minus 2 sigma on each side. So this contour gives you a contour that contains 95% of the liquid presence probability. And as you can see, it's fairly linear. So we can do a fit, and that gives you a very robust way to define an initial spreading angle from the slope of those feet, and the crossing location of those feet gives you a virtual origin in analogy to what you can do with just a single phase turbulent jet. So now we can look at the evolution of this initial spreading angle and virtual origin with the momentum ratio. So with the increase of the gas speed, if we look at the black symbol first, you see a decrease that's due to the narrowing of the spray as a gas jet has more and more momentum. And what we can see is that, as expected and as has been reported before in the literature with different definition of jet angle, you have a spray that gets wider and wider with the addition of swirl in the gas core flow. So now we're going to go a tiny bit finer scale to like the mesoscale, if you'd like, and look at the liquid core length, which from the high-speed imaging, as illustrated on this snapshot, is defined here. We use thresholding. We can detect the liquid jet, and we can look at this liquid core, so the portion that's still fully connected to the atomizer, and we can look at its longitudinal extent. So we can do that on each frame, and we get time series of the liquid core length. So the first thing that we can do is look at the priority density function. And here I report a priority function for two different momentum ratio and the same momentum ratio, but with and without swirl. And there's also dashed line that corresponds to normal distribution. So what you can see is that the normal distribution, they're close to Gaussian. The PDF are close to Gaussian, but not exactly. They're actually very well fitted by skewed Gaussian, which means that there's a slightly higher probability to find large lengths and a slightly lesser probability to find small lengths. And this is true throughout the range of momentum and swirl ratio explored. So now let's compare the square and the circle. So going from momentum ratio 25 to 80, and what you see is the distribution goes to the left and narrows. So you have a large decrease of both the mean and the standard deviation. You can have similar effect, but in a lesser extent by going from the square to the triangle. So same momentum ratio of 25, but swirl addition with a swirl ratio of 0.5 with those blue triangle. So before looking at the evolution of those two metrics, average and standard deviation of the liquid core length over the whole range, let's also look at the temporal dynamics, where here there's a sample of a part of the time series for momentum ratio of 25. What you see here is that there is a large fluctuation at a small scale. And this black line is a sliding average to look at kind of the intermediate frequency or slower frequency dynamics. And you see kind of oscillation here. And you can see the signature of the oscillation if you look at the power spectral density here on the right, where you see a clear peak that gives you kind of a characteristic frequency of this dynamic. But you can note that this peak is fairly broadband. If you move to a momentum ratio of 25, but with swirl, you see this peak kind of moving to higher frequency. But now, if we increase the momentum ratio to 80, to go to the green curve here, what you see mostly is a plateau and then a power law decay. And while you still can pick out a frequency by taking the mean of the power spectral density, this becomes really hard to tell whether this is a really characteristic frequency of your liquid core length dynamics. So the method starts to fail as those frequencies move to higher and higher range, and it's debatable of whether they exist. So we're going to move to another method to try and extract a time scale that is characteristic of the liquid core length temporal dynamics. And we are going to move to autocorrelation functions that are defined here over the time like tau, and that are taken from the centered quantity, so the intact core length minus this mean. And you see the three functions here for the same condition as before. What you can see first is that at low momentum ratio, where you have those oscillation, and this peak at low frequency, you see this oscillation dynamic of the autocorrelation function as expected, while at high momentum ratio, you see an asymptotic decrease towards zero, in relation to the plateau at low frequencies that we saw on the PSD. So now let's zoom toward a small time lag to look at the decorrelation dynamic, and you see that you decorrelate a bit faster with swirl and much faster when you increase the gas to liquid momentum ratio here. So we can characterize that. We can extract the time scale simply by taking the integral of the function, which is non-dimensional, up to a certain threshold, and that gets you a correlation time, and we can look at how this correlation time change with momentum ratio and swirl ratio, along with the mean and standard deviation of the liquid core length. So let's first look at the black square to just look at the evolution in the absence of swirl, where you see a decrease of those three metrics as you increase the momentum ratio as expected. And now we can focus on the role of swirl. So first, I'm going to highlight those symbols. For a swirl ratio of 0.25, you basically see no effect of a little swirl addition on the spray. And this is due to the well-identified lower threshold for vortex breakdown that exists in a swirl gas jet that has been reported in the literature. And we start to see an effect at swirl ratio of 0.5. So our first threshold is comprising in between those two values here in good agreement with the literature. Beyond this threshold, what we see is a decrease of the mean, standard deviation, and correlation time of the liquid core length. But now I want to draw your attention to the very high value of the swirl ratio, so swirl ratio 1 at low momentum ratio, where those gray star comes back to on the black square, so in the absence of swirl, and here for the correlation time scale, you even have something where the correlation time is higher. And we believe that this upper threshold for the effect of swirl is due to the vortex becoming unstable, and you actually would have vortex breakdown inside of the gas nozzle, inside the atomizer, instead of behind the liquid core, so you can't have this expanding effect that changed drastically the metric. But within those two identified thresholds, we can say that both the mean and standard deviation of the liquid core length and the correlation time scale decrease with increase of momentum ratio and swirl ratio. And now I want to focus on just this star at a momentum ratio of 80 and swirl ratio of 1 that has the dynamic of the mean and the standard deviation are as expected, but here we have an unexpectedly high correlation time scale that's actually about the same as what you see for a momentum ratio of 25. And here is what it looks like. So you see a very, very short and very dynamic liquid core that's shedding a lot of droplets. And so since this result is surprising, we want to look into it a bit deeper, and we are going to use Synchrotron X-ray. And to do so, we use a synchrotron at the Advanced Source at Argonne National Lab. And we use two different types of measurement. The first one, which I'm not going to talk about much, is focus beam measurement. It's a very powerful measurement where you focus the X-ray beam into a point-like measurement, basically. And thanks to that, you have very high energy, and you can use filters so that the beam is purely monochromatic. And that allows you to use Beer-Lambert law to directly measure the what is called the liquid equivalent path length. So it's the integral along the beam of all the mass of liquid that was in front of it. And so it's an absorption measurement, and you get very accurate and highly resolved time series of this EPL. But so far, I've been talking about high-speed imaging, where we need a larger beam so that we can look at the spatial correlation of the images. And so we need a larger field of view, so we cannot focus the beam. And unfortunately, it's typically not high energy enough to be able to use filter, so the beam becomes polychromatic. And now the grayscale images are going to relate. They can't relate directly to the equivalent path length. They actually measure what is called the optical density, which is a product of the absorption coefficient here, that is wavelength dependence, and the equivalent path length. So this measurement is not directly quantitative, but it's still very interesting, and you can get a lot of information from it, as I will demonstrate here, showing a snapshot at a wide range of conditions. And also a snapshot, you see a black line here that corresponds to the atomizer exit plane, and this is schemed here to kind of guide you, where you see here the inner and outer wall of the liquid nozzle, and you have liquid injected in the center, and here you have a part of the annular jet around you. And this is a very zoomed in measurement. There's only this plot here that is further downstream. So first, what we can see on all of these images is that there's lighter pockets that actually corresponds to the presence of air bubble in the liquid jet. And those don't come from injection. We can actually image through the nozzle thanks to the X-ray, and we can see that there's no air coming from here. Those actually come from interfacial perturbation that, instead of leading to breakup event, reattach to the liquid core and entrap bubble in the process. And we find it interesting to see that we can find air bubbles still further downstream and even further downstream than that. And we can find them in liquid film or ligaments. And we suspect they may play a role on a secondary breakup mechanism, but that's not something that we had time to focus on so far. Other features that are interesting to note is, for instance, back breakup, where you can see here a very poorly contrasted liquid feature that is due to the fact that the bag is a very thin liquid structure, so it absorbs very little of the incoming X-ray beam. And you can see here a millisecond the bag has broken, and you can only see the remnant of the rim here. So those conditions here, momentum ratio of 6 and 29, I'm going to classify them in a case where the liquid core is denoted as intact, in opposition to high momentum case where the liquid core is actually hollowed in the center, and we are going to refer to it as a crown, as the liquid core shed ligaments from its periphery, kind of giving this idea of a crenellation and the corona appellation. And you can see this being highlighted with a blue contour. And you can imagine here that you have the high-speed gas jet with gas recirculating behind the liquid crown and pulling ligaments from it. What you can see here on this next snapshot is a lighter pocket that I'm going to highlight, where this actually corresponds to the liquid crown, partially deweighting from part of the liquid nozzle periphery. And now if you take the same condition but add angular momentum, so with a swirl ratio of 0.5, what you see is a drastic deweighting on a large part of the liquid nozzle periphery, so that the liquid core kind of form only a crescent shape. And you can imagine this as a gas recirculation pushing the liquid to one side of the liquid nozzle. And this is what we are going to call unstable chrome. So before we dive into this unexpected phenomena that, to the best of our knowledge, has not been reported in the past, let me open an experimental parenthesis to calibrate the optical density wide beam imaging movies into EPL movies. And to do so, I use the focus beam as a gold standard. And so on my calibrating movie, I can, for instance, draw a profile on a mini EPL map that I can obtain and compare it to what I obtain by raster scanning the nozzle in front of my focused X-ray beam, where I get the gold standard mini EPL value as a function of the transverse distance. And this is the black dashed line here, and those two color lines are two different representations that we obtain with the calibrating wide beam movie, and you see very good agreement. So that allows us to validate our empirical calibration and display EPL movies, as you can see here at low momentum ratio with interfacial instability and bag formation on this movie here, and on the next movie that is going to start soon at momentum ratio of 90 and swirl ratio of 1, you see this unstable crown that's shedding ligament and is moving around the periphery of the liquid nozzle. So we are going to focus on this dynamic on a movie that's even more zoomed in, for a very high momentum ratio of 200 and a swirl ratio of 1. And here, to guide the eye, I put the inner and outer wall of the liquid nozzle on each side. So you have liquid in the center, gas on the side. And since you measure directly the the EPL that relates to the mass of liquid that is integrated along the beam. You can actually measure the center of mass of the liquid core. And I report here with a vertical red dashed line its Y location, so its location protected along the transverse coordinate. And this is going to also be displayed in this plot as I play the movie here. And with this projection to the X-ray beam, we see this liquid core being on this side of the periphery of the liquid needle to the right side, our right side, and then it's going to quickly rotate and stay on our left side for the whole duration of the rest of the movie, while still shedding ligament in a very active manner. So we can actually look into that in a bit more detail by imaging through the liquid nozzle, and you have a snapshot of that here, where once again the liquid nozzle wall are highlighted. So this is this kind of grayer area here that's not very well contrasted, and in the center you see this dark region that corresponds to liquid. And what you see is that in this dark region there's a lighter pocket, and that is due to the gas recirculation penetrating inside of the liquid nozzle, and that is forcing the liquid to be able to exit to only the rest of the remaining section of the liquid nozzle, and that is creating this unstable chrome. And so if you can think about it as this very high-speed jet is seeing the liquid nozzle with its very short intact length as a backward-facing step, and so you have this recirculation cavity. And very similarly to the wake instability behind a bluff body, this gas cavity can move around along the circumference of the liquid nozzle, and that is what is creating this unstable chrome dynamic. So thanks to this quantitative imaging, we can draw now a phase diagram of the mode, the state of the liquid core in the near field, defined as either intact core, chrome with a partial deweighting, or unstable chrome. And this is reported here in a momentum ratio and swirl ratio parameter space with a dashed line to kind of guideline to guide the eye on those transitions, but we need more points to define them more accurately. So what we can see is that this unstable chrome is only present when we have swirl in the gas core flow. And that swirl is actually a very efficient way to transition to more active state of the liquid core, even at low momentum ratio value. Here you can see at 25 that at swirl ratio of 0.75 you can reach this partial deweighting, which you will need to put in a momentum ratio of 200 to reach it here without swirl. Now I want to draw your attention to those points here that have a hollow center, hollow white center that are actually conditions that we explore in the without swirl, but by variation of the liquid injection rate. And those are done by modifying both the liquid injection rate and the gas injection rate, so that we explore same value of the momentum ratio as before. And we found actually the same mode as the condition before. So we can say that when varying both the liquid injection rate and the axial and tangential injection rate for the gas, so for those three parameters, this phase diagram is fully captured by the only two non-dimensional parameters, swirl and momentum ratio. So now let's look back to the unexpected results that we saw in the temporal dynamic of the liquid core at high momentum and swirl ratio, which is remaining here. So now we know that in this, while this is harder to see on the high-speed imaging, this corresponds to an unstable liquid core dynamic, liquid chrome dynamic. And we're going to look at it in a bit more detail using the backlit imaging with visible light, where, of course, we don't have access to the mass, a direct measurement of the mass of the liquid, but we still know the liquid's presence, and we can do much longer movies because we don't have the same constraint, experimental constraint as we have in the synchrotron. And so we can get the contour of that and do a center of area of this liquid core and get time series of this center of area. And we can look at the power spectra, which is displayed here in black in the absence of swirl, where you see a plateau at low frequency, then a peak at moderate frequency that corresponds to the flapping that we've been describing earlier. And you can see that the story is very different in the presence of swirl here with a swirl ratio of 1, where we had this weird temporal dynamics, where you see maybe still a signature of the flapping here at slightly higher frequency, but what's very surprising is to see this power law at low frequency that is associated with the emergence of a long time dynamics that is due to the motion of this recirculation around the atomizer axis. Well, to go a bit further, I represented here the correlation function of the liquid core length in solid lines, which corresponds to what we've been talking about before, where adding swirl here actually gets you a decorrelation that's a bit longer than in the absence of swirl, which is expected. But you can compare this decorrelation dynamics with the one of the decorrelation dynamics of the center of area here in dashed line, where you see that this is taking forever to decorrelate, and that corresponds to this power law in low frequency in the power spectral density. So you can see that those functions are clearly not alike. They are quite far from each other. So that tells you that the vortex dynamic does affect the liquid core length by making its decorrelation a bit slower than expected, but it doesn't fully drive the liquid core length time scale as those functions are far from each other. So now, before concluding, I will touch briefly about spray feedback control, since this work was done in the context of a multi-university research initiative funded by the Office of Naval Research, whose goal was to demonstrate the feasibility of multiphysics control of atomization. And the role of the University of Washington was to lead open loop investigation of different actuation to develop reduced order models to establish feedback control. And you can see more detail on that with the control using swirl, so actuation of the flow rate, and also electrification of the nozzle. And we have a work in progress with acoustic perturbation of the spray. So I will touch briefly on the control with the swirl, since it has been the focus of the talk today. So now we have this coaxial atomizer where you have two inputs, the tangential flow rate and the axial flow rate, and you want to control the spray feature in real time. So typically, it's very challenging to do real-time measurement with a high-speed camera. So we move to a line CCD camera where we can obtain a profile of the spray in the far field in real time at a rate of around 800 Hertz. And here we're just doing attenuation along the spray, so like the backlit high-speed imaging that I've been presenting so far. We also tested scattering, and that was actually very successful too. And so you can get an attenuation profile that looks like that, as you can see here, in black with a low momentum ratio spray, and in red here you have, in blue you have the higher momentum ratio spray, and now you have the same condition in the presence of swirl in red. And we noticed that we could do proper orthonormal decomposition on those profile and use only the amplitude of the first three modes to very accurately reconstruct the profile, as you can see here with a dashed line for the three condition over the, so this worked well over the whole range explored. And so now we're left with having to only characterize the variation of amplitude of those three modes along with variation of those two inlets. So we have a two inputs, three outputs plant model to derive. And so once this is done, so this has been implemented in LabVIEW, as you can see here, where I will show this movie where in white and red you have respectively the axial and tangential flow rates with the time being displayed here in a second. Here in green you have the real-time measurement of the absorption profile, and in yellow you have the goal profile that can be set by the user and that was randomly generated. And here you have a root mean square error between the goal and the measured profile that serves as a gain in our model. And here you just have with an additional camera a real-time visualization of the spray profile just for the sake of this video here. So so now here we start with a fairly low momentum narrow spray, and now the user sets a new goal profile to reach, which is reached in a matter of several seconds. And then the user is going to change to another option that corresponds to a pretty dense and wide spray, which is happening now. And you see the profile going close to it and staying there. And here we go. Now we are moving to this dense spray where you see the system reacting very quickly and overshooting actually, and then within a few seconds converging to this desired profile. And now we're gonna switch to a very low momentum narrow spray, and you will see the control once again reaching pretty quickly in a matter of a few seconds the desired profile. So I will conclude now. So thanks to the high-speed imaging, we are able to see a complex dynamics of the liquid core length with non-Gaussian distribution and strong correlation. And we saw that both the mean standard deviation and correlation time decrease with increase of momentum ratio and swirl ratio, with of course identified threshold, upper and lower threshold for the swirl. The Synchrotron X-ray high-speed radiography illustrated the fact that there is a fourth state for the liquid core that depend only on the two parameter momentum and swirl ratio, and we observe this unstable crown only in the presence of swirl. And we saw that the state of the liquid core affects the liquid core length dynamic quite drastically. And then we demonstrated the ability to achieve a real-time feedback control using a two-input, three-output plant model. So with that, I will thank you for your attention, and I will gladly take any question.
Thank you very much, Nate, for a very interesting talk. For the audience, if you have any questions, you could unmute yourself and ask it verbally. And if you'd rather not do that, you can type your question into the chat, and I will pass it along to Nate. So I'm also looking at YouTube to see if there's any questions on YouTube. You're welcome to post them there as well. But if you have questions, please unmute yourself and go right ahead. So Nate, while people are thinking of questions, I have one for you. So you have this unstable crown where in your projection images, it looks like it's sliding back and forth, but in reality, it's probably doing some type of helical motion. And I'm wondering, is that unstable portion, is it always moving in the same direction, either clockwise or counterclockwise, or does it switch directions?
So yeah, that's a good question. I think that by doing high magnification imaging, backlit imaging with visible light, that's something that we could answer because we could do, let's say, 10 different realization and see with that level of statistic whether or not this is always the same direction or not. I I don't think we can answer that with available data that we took in Argon, because I don't think we have quite the level of statistics. I would tend to say that with the swirl, you do deviate from coaxial, like pure axisymmetric flow, since you have this helical jet. So you may well have a preferred direction of motion of this vortex.
Okay, thank you.
Ed, can I ask a question?
Please go right ahead.
Nate, nice talk. I know that I'm sort of part of this work, or this MURI, so I've seen parts of your work. But one sort of philosophical question. You talked quite a bit about swirl, but the groups have also looked at other means of controlling the spray. Do you see, in terms of recommendation, from both implementation point of view, also from a controllability point of view, do you see swirl versus other controlling mechanisms advantages, one certainly winning over the other, etc.? So I just wanted to ask you, in terms of controlling the spray, what your thoughts have been.
So I think swirl is a very, very powerful mean with a fixed total gas flow rate to have drastic change on a spray. And this is something that is known for a long time in the application side of atomization. And in many applications, you have swirled atomizer. That being said, this type of swirl atomizer are typically obtained from the geometry of the atomizer that can have groove, for instance, so that the swirl is fixed and that is kind of at an optimum point for this system. So, so here the swirl is more like we want to understand what it does, but we cannot use it as an independent knob to tune our spray. And there, I think, is where an electric field or acoustic field additional perturbation could allow you to finely tune your spray and offer a different parameter space. And with both of those means, we were also able to change the spray efficiently. But I would say that yes, swirl is very efficient at modifying the spray, both in the near field and far field.
Ted, I see some questions on chat.
Yep. So Nate, on chat, there's a question. Nice talk. Have you considered liquids other than water? And what's the sensitivity to modifying the density ratio between the gas and the liquid?
So yeah, we've stayed on water mainly for practical reason, but also here we are interested in very high gas momentum jets, where it's gas-assisted atomization and the turbulent gas jet is dominating the atomization mechanism. So especially in the near field, surface tension does not play a significant role, and the gas momentum is the main parameter. If you're looking at secondary breakups, then change in the liquid properties and surface tension, for instance, will indeed play an important role too. In terms of density ratio, from the top of my head, I don't know an efficient, like right now we are about the liquid is about 800 times denser than the gas, which I know can be a challenge sometimes for numerical simulation. But I cannot think of a way with staying with those type of fluids, like close to air and water. I don't know of a good way to change that. You may need to go like to cryogenic condition, for instance, to change this ratio drastically.
Thank you. Are there other questions for Nate?
Yes, I'd like to ask a question.
Go right ahead.
So the very interesting topic, but I was curious of if you put the water on the outside and the gas on the inside, do you get a different story?
I know that there is a lot of studies on those type of geometries, and I'm not very familiar with that, so I don't want to give you a wrong answer here. I believe that typically in this case, what you have is that the liquid width is you are more or less a liquid film, and then you have film breakup that is more similar to like those back breakup mechanism, and you have less so those fiber type atomization. So that's where I can say that there should be a difference. We really have like a thick liquid column that is being destabilized on the side. So you have atomization phenomena that happen really on the side of this liquid column on top of things being peeled from the end of it. So
you introduce the water tangentially in a stationary tube. So it's kind of like a cyclone or something to enter the water. Did you ever do any experiments where you rotated the tube, the solid tube, and then just put in the two fluids? You don't add that except for the boundary condition at the tube.
Yeah.
So is there an interesting story there?
I believe that there's extensive work with the swirled liquid condition where you put a kind of a helical groove pattern inside of the liquid injection, and that changes kind of the right at the outlet interfacial condition, and that can change the type of interfacial instability that develop at the beginning of the near field. But
yeah, everything
to
changes qualitatively, and I just was wondering if there was a practical reason to study all three cases.
Yeah, I mean, I believe that geometry does play a large role in those atomization phenomena and in going in those transition between regime and all. And this is kind of why we try to redesign a very canonical coaxial atomization scenario where we can look at those mechanisms and the underlying physics, and we didn't focus on changes in the geometry, but that I believe that there's room to look at that for sure.
So when you do an analysis on your experiments, do you ever consider doing a two-phase flow and just call it and then use your information that you're having to understand a two-phase flow model better than we now understand it?
So I think
your analysis of what you're saying is yeah.
So yeah, I think that would be really interesting. That's a really interesting question. Unfortunately, with backlit imaging, as you see being displayed here, whether it's with X-ray or visible light, you only have the information about the liquid phase. You have no information about the velocity or mass of your gas phase. So you would need to do actually velocimetry measurement that are synchronized to those type of imaging to really get an information about this two-phase flow and be able to model it adequately. And there's for that a lot of experimental challenge arise, but that's a really interesting direction to take for the future for sure.
Okay, I'll stop now and come back later. Okay.
Yeah, of course. Thanks.
So
Okay.
Nate, there's another question on the chat regarding the density ratios. I just lost it here. Just a second. Couldn't you use a high pressure environment to change the density ratio?
Yes, of course. Thanks. That's a very good question, and this is actually the direction that the Multi-University Research Initiative is taking, where Ted Heindel group actually created this pressure vessel that is fitted to study those atomization process, and great detail has been taken in the design of this to get this very nice coaxial spray, but where you can also image using either the high-speed imaging with visible light or in the synchrotron that comes with a lot of constraint, and also doing laser interferometry in the far field. So this, I think this is very exciting, and I can't wait to see the results that we will be able to obtain there. So yeah, thank you very much for the question.
So another question from the chat, great presentation, and it's impressive to control the spray manually. I have a question about what could be the final expectation of the spray control. Since this control mechanism seems to be mainly designed for fuel spray combustion, do we expect the spray droplets to be distributed as widely as we can control, or is there an optimum distribution that the control can achieve for the best overall combustion efficiency?
So yeah, thanks. That's a very interesting question as well. Right now, what we focused on was demonstrated the ability to control in real time the structure of the spray in the far field and in a wide range of way, because of course combustion is a very important application for propulsion, but there's also a different application. Maybe for coating you want a very focused spray, or maybe you want a wide spray with homogeneous distribution. I think it depends widely on the application, but I think that there's room to interface and do the end check with the combustion community to try and see what would be for them the goal inlet condition for their models, and see if we can reach that with our tools here. And that could be very interesting, and see, for instance, if you can keep this control when you, for instance, using the pressure vessel to come and do perturbation in the pressure, such as you can have in an airplane when you have a change in altitude due to turbulence, and see if this the control is stable versus those perturbation, and also so that would be really interesting to check.
So to follow up with that, is there a way to measure particle distribution in real time that you can use in the control?
So I believe that with the light scattering measurement, we can get a very good proxy of that. You're not going to get something as you would get from raster scanning, laser interferometry measurement over several hours on your spray, of course. That's not going to be on this level of detail, because that wouldn't be real time. But I think that by the scattering measurement of a light sheet that's going through your spray, you can get a very, very good proxy of the distribution, the flux distribution in your spray.
Okay, thank you. And I have a question from YouTube. Very interesting talk. Can you make a comment on the spray control using the electric field?
Yes. So what we do here for the electric control is that we have two plates on the side that are charged at a high potential, and we inject for those conditions to see a large effect on the spray. We inject water with addition of salt so that the conductivity is higher, and we manage to do induction charging on the liquid, and this can get you into kind of similarly to the swirl here. You can get to more absorption and wider profile. So a denser, finer spray that's a bit broader when you do those kind of things. And there's more detail in this 2020 atomization and spray paper, and I would be also happy to chat about it after the talk too.
All right, thank you. So are there any other questions for Nate? All right, well, again, Nate, I'd like to thank you for a very interesting talk. This is a great way to cap off our first series for this Spotlight Seminar series. And I want to, again, remind the audience that we will be taking a break for the summer, but we're going to be returning in the fall, probably in mid-September, and we'll have kick off with a well-known keynote speaker, and then we'll have some young up-and-comers in multi-phase flow give the remaining talks for that semester. So Bala, did you want to say any last words before we go?
No, not really. You summarized it very well, Ted, is that we look forward to another successful round of talks in fall. Yeah. I want to thank all the speakers and Andrea Prosperity for initiating this round of Spotlight seminars.
Yes. Thank you all.
Thank you very much.